What is a weak head normal form? In the implementation of, for example, some languages such as Haskell or Miranda, a lambda term is not evaluated to normal form, but roughly to weak head normal form. A weak head normal form, abbreviation WHNF, is a lambda term which satisfies some properties. The first property or the shape of this lambda term must satisfy this thing. Then you have some lambda x dot p. The p is some lambda term, absolutely any term. If we find that our term is satisfy this pattern, they say that it in weak head norm in a weak head normal form. This was the first pattern. The second pattern, then they have the form of xp1 till pn. The n is greater or equal 0, and p1 to pn some arbitrary lambda terms. So absolutely any lambda terms, but at the first position must be some variable x. And actually this is the definition of the weak head normal form lambda term. And we also can give the definition of the set of all normal forms similarly. A normal form is a lambda term of one of the following two shapes. It can be represented as a lambda x dot m, with m the m is a term, but this term must be in a normal form. So actually we can't do any more reductions here, better reductions. And the second form is, as in the first case, we have this x, first term, and after this m1 till mn, with n is greater or equal 0, and m1 till mn all the normal forms. So this means that they can't do any reductions. And every normal form is a weak head normal form, but not every weak head normal form is a normal form. So let's review some examples. For example, take this identity lambda term. This is a weak head normal form and also as a normal form. So why? Because it satisfies this property of a normal form and to this property of the weak head normal form. If you look at this term, so we have some lambda x dot identity of x. This is a weak head normal form. Because why? Because it is satisfy this property. But it's not a normal form. Why? Because the body of this lambda can be reduced. But in a normal form, it must be in a normal form. And so on. You can see here, for example, lambda x. This thing, it doesn't have a normal form at all. Why? Because this combinator is defined like this. So it is actually has it can be reduced because it repeats itself again and again. This example, just x, some variable x, this is a weak head normal form. It is also a normal form because it satisfies the number 2 property. So we have this this pattern here or this pattern here. Actually, we have this situation that the n equals to 0. If we have x applied to identity of x, this is a weak head normal form. As a normal form. So this thing, this thing is a weak head normal form. It has weak head normal form, but it has not a normal form. Why it has a weak head normal form? Because we in situation like this, and we have this p as an arbitrary lambda term, and this is a reducible lambda term. But it is a not normal form, because we can't apply this rule. So has x here, but here they must have the normal form term. But here they have the identity of x, which can be reduced to this thing can be reduced to x itself, and that's why it is not normal form. And the next situation, if they have this x with this combinator, this is a weak head normal form because it satisfies this property. But it doesn't have the normal form because we can reduce this thing. There is infinite steps of reductions can be done here, and that's why this weak head normal form does not have a normal form. But for example, here this weak head normal form has a normal form because we can take this weak head normal form and do the reduction inside it with this identity combinator. And for example, this thing has a weak head normal form, but hasn't normal form. So we can again do this reduction infinitely many steps. And for example, here this weak head normal form has a normal form. Why it has a normal form? This thing. Because we can reduce this thing and go to some term which can be reduced anymore. So only by one step we can do this. So we can explain the intuition of the weak head normal form in this way, that a term where the first part of the result can be rid of. Indeed, no matter how the term lambda x dot p is further reduced, will always remain of the form lambda x dot p prime or some p prime reduct of p. So with some this beta relation, beta reduction, which is actually the so we take beta reduction, add to it reflexivity, symmetry, and transitivity, and we have this relation here. And this is for the first situation. And if we look at the second situation, no matter how the term x p1 till pn is further reduced, it will always remain in the form x. This x will be always at the first position, and we have this p1 prime till pn prime, and these primes are just adjust this better relation to initial term pi for all I from 1 to n. So this thing is actually the transitive symmetric reflexive closure of beta reduction.